get in somehow. So finally, I was able to handle that. Okay. So just some logistics before we continue. So as you probably realized, I already graded homework 3 and homework 4. Homework 4 I didn't actually grade, but I give you the assigned grades. So with that being said, I want to make sure that you guys keep up with the reading and review solutions for the homework, so that you know what type of solutions I'm expecting. As the email that I sent out recently, I mean, later last week, I specifically mentioned that you should do, you should have graphs, you should have code, you should have some discussion about results. I think some discussion about the results is rather important. For any analytics work, I think it's rather important to have the discussion there. Okay. Any questions so far? No questions? Okay, so if no questions, I'll just continue with the slide set. Somehow we don't have a lot of people today. Is that because I was late and people just dropped? Or everyone is busy because of the mid of the semester, almost mid of the semester. It's not quite yet there though. Okay, so let me pull up the slides. So your question is linear programming solution for the regression question in one of the homeworks. Oh, I see. Sure, you could. That actually I really want to discuss because a lot of you guys actually didn't do it correctly. It's not linear regression, it's really for the, let me pull it up actually, hold on. Okay, let me share my screen. For this question, I'm not sure if, Derek, I'm not sure if your question is related to this one, but if not, you can post in the discussion section and then I'll try to respond. But for this question, I really want to go through. First of all, see here, what we are after is, we're saying that, okay, we're trying to fit this line, but the objective function is not to minimize the predicted value minus the actual value squared. We're not trying to minimize that least squared error. That's why it's not linear regression. So the objective function is trying to minimize the largest deviance between the data and the line. So remember that we actually went through one of the examples for the measuring of two segments in class, A, B, C, and then try to minimize that deviance of the measurement and the actual value. This is identical with that. That's why if you look at here, if you look at this problem, you see some similarity between this one and the one that we discussed in class. And then it's trying to minimize something, which is something R is the absolute value of the observed and the function value, right? So it does have a similarity between those two. And then at the end, you can translate into a function form of this. And then now it becomes a linear programming problem, but you are not able to solve it quite yet using this function. But I want to mention that some of you are actually trying to fit a least square linear regression model for this problem. That's apparently is wrong. Because for linear regression, the objective function is always the minimization of the least squares. Okay? How to use linear programming, because we haven't learned it quite yet. So you would know it, I think it's actually today, I believe, later in the section. Okay? We do this question, it's probably a stretch because I haven't, depends on what's the approach that you're going to use. If you use a computer program, it's straightforward. If you use a simplex by hand, then I didn't prepare for that quite yet. So let's go there and then try to go through the simplex method, and then it would be apparent this is a linear program. Okay, Derek. So we can continue on this. Now today we're going to slide set week 5. So this section is actually rather straightforward. Okay, we talked about linear regression in this section, but the previous sections we didn't actually touch upon linear regression quite yet. So it's a good point that we went through why that question was not linear regression, but here we would see what is a linear regression. And also we talk about probability modeling with discrete systems and modeling system reliability. So previously we actually studied developing models using proportionality and determining the constants of the proportionality, which is the beginning of the semester, first 2 or 3 chapters. Right? In this chapter, we are going to allow the constants of the proportionality to vary in a random fashion rather than to be fixed. Let's continue. Actually, by the way, if you cannot hear me, let me know because I'm using can you guys still hear me okay, or? Yes? Okay, what I'm using here, hold on. So you are hear me okay, right? Yes? Okay. That's good. Okay. Give me 1 second, 1 minute. I'm trying to charge my my speaker, so I put things together. Hold on, give me one minute. I'll be back. Okay, so let's continue with this. So in this chapter, we're trying to allow the constant to be of the proportionality to vary in a random fashion rather than to be fixed. So in one of the material that I posted in this week, I believe it's in this week or the week after, next week's sections, you would be able to find something that I call MM1Q. So that specific set of lecture notes can help you to understand similar issues here, because last time we discussed the queuing system as well, how the arrival time, how does that change, how does that affect, but we didn't actually touch upon how we can use a math model to analyze the queuing system. But at least we give you a perspective in what scenario you want to leverage a simulation model to solve your system problem. But in this example, it's an analytical model. So for example, rental car problem. If someone is if two locations, one location one and location two, let's assume it's one is Orlando, Florida, the other one is Miami, Florida. So what happens is someone potentially could rent a car from location one with a certain probability that he returns the car to location one as well. This probability is P. And on the other end, there's a potential probability that he would return a car to a second location, which is location 2. And then with this probability would be 1 minus P, meaning that when he rents something from 1, it eventually will have to go somewhere. It's either coming back to 1 or going back to 2. So apparently this is a rather simple model because we only have 2 states in the system, right? Similarly, on the other end, for location 2, there's a probability that he returns the car to location 2, and also that probability is Q, and then there's a certain probability that car would be returned to location 1. So that's a problem. And then what we want to do is assume that at the beginning of the year, there's a total of N cars. And then in the long run, what's approximately how much of the percentage of cars would be in Tampa and how much percentage of cars would be in Orlando. So you can see that based on the math equation, you can see that the probability that we're trying to measure is, suppose that initially there's Pn cars at time n, there's Pn cars in 1 and Qn cars in location 2, and then how many cars is going to be staying Q, this particular location at the next time step, right? That would be the probability of the cars that's staying in this state, and also the cars that is coming from a different state, which is coming from location 1. So the reason that we call it state, because this is one of the states in the system. So if you think about what we talked about the queuing system in MM1Q, which is exponential interarrival time and Poisson exponential service time as well. And then if that's the case, we can use number of customers in the system as a state. And then in the system, it can be 0, can be 1, can be 2, can be all the way to n. And then there is a transition probability between 0 to 1, 1 to 2, 2 to 3, etc., so that we would be able to build MM1Q model, which is rather similar to this, except that that model has a special feature of the arrival distribution and service distribution, so that it has closed form analytical solution. This one also, of course, it has a closed form analytical solution as well. And then here, another example is very similar, except that now we have 3 states.
so that we can set up 3 equations trying to figure out what's the long-term probability of all these voters, long-term probability that how many of them would be voting for different parties. So this should be clear, right? Okay, and then in terms of component and system reliability, reliability is really defined as 1 minus the probability of failure. So capitalized FT is the failure rate, failure probability, and then if we 1 minus that failure rate, then the rate would be the reliability. Let's see how potentially we can do the reliability. And then for the reliability for a series system, you can use just the multiplication of each individual reliability of each individual components. And then for a parallel system, you would use this equation, which is similar to the Ohm's law that we learned in high school, right? So it's the first one plus second one minus first one times second one would be total resistance for the for component system if it's parallel, right? So and then for series and parallel, you just look at the first component reliability times second component reliability so that you get the system component reliability. And then the first subset could be a series system, and the second subset could be a parallel system, or the other way around, or could be 2 series systems as well. Okay, so that's rather straightforward, which is also covered in the textbook in much further detail. Now let's talk about linear regression. So basic linear regression is really we're trying to fit this model, and then before we go to the normal equation and best fitting line, let's go to next slides. What we're trying to minimize is something called sum squared error, which is error sum of squares, which is the first component yi is the actual value that we observed. And then the second component is coming from the prediction of the equation that we estimated. Because we're trying to estimate this equation here, A and B, based on xi and yi, all those observations, right? As you can see, if x-axis would all the x's, y, if we have 2-dimensional, we have multiple points, each point has corresponding x and y, and then we're trying to figure out, let me use a pen here, if I could draw something. No? Oh, yes, I could. Okay, so assume that we have a bunch of points, observations, so that for each point here, correspondingly, it will have a x value, x1, and corresponding of y1 value, right? So that's the whole idea if we have xy 2-dimensional space. And then the question is, we're trying to fit the best fitting line that would kind of passing through all the points, and then where this line should be. And then in order to determine this line, as long as we determine the slope and the intercept, which is the A and B, then we would have a unique solution for this line, right? So the idea is really that we're trying to minimize the actual observation, which is here, and then the predicted value. Assume that this is our line, so the predicted value of x corresponding on this line would be here. What we're trying to minimize is the difference of those two values, and also difference of here, difference of here. For each point, we will have a difference, right? And then we use this, which is called error term, and then this error term squared is the objective function that we're trying to minimize. That is sum squared error, which is the observation minus predicted value squared, right? Okay, so assume that we set up this equation, set up this objective function, and then how can we solve it? one way that we can solve would be take partial derivatives in terms A and in terms B, so that we can set up two equations to try to solve it, right? Because remember that in order to find a minimization of quadratic function, what you do is take first order derivative. But in this case, because it has two unknowns, if we take first order partial derivative of A and of B, we can set up two equations. And then if you do that, it happened that on the previous slides, we would be able to find two equations, set them into zero, and then find those two equations. Those two equations are called normal equations. And then, based on those two normal equations, you can solve for your A and B. A and B is a function of all the observations xi and yi, as well as m, which is the number of data points. So that gives us the best fitting line that we are after. So hopefully this is clear, so that if you read through the textbook, you would definitely understand much better. Here I'm just trying to guide you through to give you some gist of what that is. And then once you get A and B, there's something that's very important that you should know in linear regression. One of them is total corrected sum of squares. That is the actual value, which is observation. Again, there I write as observation, but it's the same as actual value minus y bar, which is y average. In that case, in this example, y average would be all the y's average value. This would be my y bar. And then if you use this for each of the yi minus this y bar, meaning that for this y minus this y bar, for this y minus this y corresponding y bar value, and then you could get all the error terms, and then this is something called sum of total squares. And then the next thing is the difference between the sum of total squares and the sum of the errors would be something called regression sum of squares. And then R squared is determined by y minus SSE divided by SST, which is equivalent to SSR divided by SST. Now you know why, if you know anything about linear regression, we're looking for something that's higher R squared, right? So that's why if higher R squared, meaning that regression is doing a good job, because the sum of squares is higher while sum of squared error is smaller, and then we are trying to minimize that value, meaning that higher square sum square of error is smaller, we are trying to find a better fitting line. That's the whole idea. Even though when we're trying to, in reality, when we're trying to build a model, there are some other considerations, not just higher R square. Potentially, we could look at how many factors that we put into the model. Potentially, if we have 20 factors that give you a nice R square of 0.91 versus 5 factors that give you a R square of 0.90, you probably would choose the 5-factor model, right, rather than the 20 factors models, because it's just more practical, especially in business setting. It's easier to collect data, to managing the whole process. Okay, so that's a very concise way to talk about linear regression. So just also want to mention more things here. That would be something we call residual. With residual would be the difference between, because the linear regression, it's really, to be precise, it should be yi plus axi plus b plus error term. So with that being said, each of the predicted value and actual value would have this error term that we mentioned. And then the way that we look at the error, how good the model is, one diagnostics of the model, the fit of the model is by looking at the error term. So what we are looking for is really that the error term is randomly distributed with a mean of 0. In other words, the type of pattern that we are looking for should be somewhere here. Some of the, but are positive, some of the values are negative, and then it's rather random. This is the type that we're looking for, but in reality, majority of the time we could be facing some of these issues. One type is the error term is fanning. With larger x, error is larger, meaning that our model is not doing a good job in this section. And then error term is linear, meaning that our error term is just much bigger, then meaning that our model is not doing a good job. And then if it's curvilinear, that's another type of curvature or pattern that we are looking for. So what we are saying that in order to improve the model, you need to pay attention to this error term. Potentially you need to transform your variables to improve the fit, to make sure that your error term is random, just like what we draw here at the bottom of the slide. Okay, that is linear regression, and that's everything that we plan to discuss for this week. Apparently, we need to go through material for next week as well. So hold on, let me find the slides. Any questions? No? Great. So let me find the slides for next week. With linear programming would be week after. Oh. Hold on. Yeah, there we go. So what we should be doing is really week 6 for next week. So and then for week 6, what we're going through is linear programming. And then the chapter in that textbook covers multiple points. One is overview of optimization modeling, followed by linear programming, followed by, which is the geometric solutions, and then followed by the algebraic solutions, and followed by the simplex method and sensitivity analysis. In today's session, we probably wouldn't be able to cover simplex method quite yet. So I'll try to cover up to 7.3. Let's see if we would be able to, so that you probably have to spend some time on yourself on simplex method as well. And then next, when we meet 2 weeks from now, I'll continue with these materials as well. So so one of the examples that we went through, Chebyshev criteria, that is the one that before we start the homework, which is the second criteria that we have. Minimize the largest of the absolute deviations, right? And then previously we already also talked about how to minimize the sum of the absolute deviations. And then also we talked about minimize the sum of the squared deviations, which is the least squares criteria that we talked about just now. And then what is a linear program? That is minimize something subject to some linear constraints. So the objective function have to be linear, and the constraints have to be linear. So this is rather abstract. And then let's see a more specific example. And then here we talk about, okay, the basic model is to optimize something. It could be a minimization problem. It could be a maximization problem as well. and then it's subject to certain constraints. That's really what is optimization about. And then if the equation, either the objective function or the constraints are linear or nonlinear, or integer or non-integers, etc., then we would have different branches of the optimization models. And then with this, I want to mention that number one, there's a decision variable or multiple decision variables in the model, such as x1, x2, x3, etc., that would appear in our constraints as well as objective function. And then what is objective function? Objective function is really optimizing something. If we're trying to minimize the sum of squared error, then that is our objective function. And then what would be the constraints? Constraints would be subject to something. And then we would have specific examples about what is constraints, so that you probably would be able to understand this much better. And then another term that we usually use would be right-hand side, which is the BIs that we see here on the graph on the slide. And then optimization problems, it can be unconstrained, it can be constrained. And then specifically for linear program, there is a unique objective function, and decision variables has a power of 1, meaning it is if we have two decision variables of x1 and x2, and then it should be a linear combination of being the objective function and also constraints, meaning that it will be 30x1 plus 50x2, then it would be linear. If we have 30x1 squared plus 50x2, then it's no longer linear, right? So that's straightforward. And then no product of decision variables in the objective or constraints. That's also straightforward because we said there should not exist any of the nonlinear component. If we have x1 times x2, essentially it's equivalent to a quadratic term in the function. And then the next criteria, the coefficients of decision variable in the objective function and its constraints are constant. That is to say, 50 times x1, for example, that 50 is that constant. And the decision variable are permitted to assume fractional as well as integer values. This is just trying to differentiate between linear program and the integer program, because integer program itself do have its unique characteristics that are different from linear program, and as a result you do have to have different solution methodologies that help you to make a decision on the integer program. For example, if we see that we can only manufacture integer number of chairs and tables, then you wouldn't be able to solve the problem with a linear program, because the linear program does not guarantee that x1 and x2 would be the integer number, right? It potentially could be a fractional number. Okay, so and then just also want to give you some general idea. There are some other types of programs. For example, multi-objective or goal programs, nonlinear program, dynamic program, and stochastic program, integer program as well. In our course here in this semester, we're going to cover only linear program, nonlinear program a little bit, as well as the last one on the list, which is the integer program. And then sometimes we also call it as mixed integer program, MIP, because some of the decision variables would be integer and some others would be just linear constraints. In that case, it's called mixed integer with linear program. That's why it's called MIP. Again, we only cover nonlinear program, integer program, and linear program. And then this is a example of just say that what is potentially what would be a linear program. For example, here, because we're not going to talk about too much detail here quite yet, so just give you a sense. potentially what it can be. For example, if yj takes only two values, is either 1 or 0, and then this is a classic something called, even though here it says space shuttle cargo, but in classic optimization problem, this is called knapsack problem. Hold on, let me get a pen. It's called knapsack problem. The background is, assume that you need to go out for hiking, right? You go out for hiking and then you have a bag that you need to carry something. You want to make a decision on, should I carry water? Should I carry some food? Should I carry something else, right? But you know that this knapsack itself has a certain capacity. You can only carry 5 pounds in there. For example, you don't really want it to be too heavy. And then meanwhile, you know that each item is going to give you a certain benefit. If you take a water, you get a happiness index of 20. If you take some food, happiness index of 10. Things in that nature, right? And then the question becomes, how can we maximize all the happiness if we bring different items? So, and then now it's a classic idea, right? Okay, if I take yj, j could be multiple. In this case, if we talk about water, food, maybe a phone, or whatever that is. This yj essentially would be y1, y2, y3. So we're saying that objective function is really c1 plus y1 plus c2 plus y2 plus c3 plus y3, right? So we're trying to maximize this. And this C is something I call it happiness index. When you have certain things in your bag when you need to use them, right? That's the objective function. And then simply put, mathematically we can say that yj equal to 1 if item j is taken. That is to say that if y1 is taken, I can get c1 level of happiness, right? That's a maximization problem as this objective function. And then what's the constraint? For example, the first constraint could be the size of the knapsack that we talk about. In other words, volume that I can carry. And then volume, total volume, that potentially, okay, I can only carry a 2 cubic, I don't know the unit, but in this case, right, we have certain volume constraints. Meanwhile, there's a weight constraints. Right? As I said, probably I can only carry 5. I plan to carry at most 5 pounds. And the decision becomes how many units of each one of them I should be carrying. Maybe 2 bottles of water. Decision could be y1 equal to, in this case, because it's 1 or 0, meaning that you only carry 1 unit if y1 happen to be 1 and y1 happen to be water. And then y2, if y2 is 0, meaning that let's don't put any food, and then y3 equal to 1, meaning that let's put a phone into the knapsack. That's the example. As also here, say it's called space shuttle cargo. It's very similar from knapsack, which is actually identical from knapsack. In classical math programming optimization problems, we all call it as knapsack. Okay, hope this is clear. And then if we look at next one, we say, okay, for a function, potentially we could approximate by a piecewise linear function. And then that's what that is, saying that for each separate section, we can fit a linear function on there. That's very normal way that you use it. You do it, and then you can set up this function, and it will be a linear function. And then next one, let's think about a carpenter's problem. Suppose that we need to make a decision on how much tables and how many, I don't know which one is table, which one is chair, but don't worry about it for now. Suppose that x1 is number of tables I'm planning to make, and then number of let's maybe the other way around. This is x2, number of tables, x1 is number of chairs that I can make. Right, and then what we're trying to say that we're trying to maximize the benefit we can get from the tables and chairs. Suppose a carpenter knows that one chair can be sold for $25 and then one table can be sold for $30, and then the decision becomes how many chairs and how many tables should I be making. And then apparently there is certain constraints that I have to make sure that they are satisfied. One of them is each of the chair that we're making needs 20 units of the lumber, 20 foot, for example. And then each of the table needs 30 foot of the, or 30 inch, or whatever that unit is, 30 foot most potentially, 30 foot of the lumber. And then in total, he only have 690. So in order to satisfy that, we have to have this relationship. Total number of lumber that would be used for manufacturing the chair and the tables should not exceed to the lumber that's available. And next question that next constraint that involves labor constraint. Suppose that the first one needs 5 units of labor and second one needs 4 units of labor, and then question becomes, if I only have 120 labor hours that someone can spend on, how can we best utilize X1? How can we best utilize the labor so that the number of chairs and number of tables that we need to manufacture decision can be made? And then next constraint after this is this cannot be negative, right? And then here, as we can see that we didn't specify them to be integers. We allow them x1 and x2 to be non-integer fractional numbers, and you can make a decision to round them up or round them down. In this case, you have to round them down, right? Because you cannot manufacture if the solution is 3.5, you wouldn't be able to manufacture 4 chairs. You should be manufacture 3 chairs. So that's a problem. And then let's look at what it is for these constraints in 2-dimensional space, with x1 and x2 being x and y's. One constraint, we know that 20 plus 30, 20x1 plus 30x2 in that 2-dimensional space equal to 690 would be a straight line, right? In this case, it would be this line. This line is really the first constraint. But we say it has to be less than or equal to that. So only feasible solutions would be coming from this side. And then what is the second constraint? Second constraint would, again, the line equal to 120 would be this line that we have here. So that's the second constraint. And then the feasible region would be anything that would be less than this number would be on this side of the line. In order to satisfy both of those constraints, you have to be within this gray area, right? And then, because we also have this non-negativity constraint, that's why this whole gray area in general is called feasible region. Okay, so that's something that we introduced here. And then next question, you can see that we already labeled here. There's some extreme points. One of the extreme point is really this A, which is 0, 0. Second one is B, which is 24, 0. The next one is C, and then the fourth one would be D. These 4 points define our feasible region. Now question becomes, what is our solution? If you look at the objective function, it's 25 plus 30x2. If we use because we don't know what this value would be, right? So potentially we know it would be a set of parallel lines. Question is, what value of x1 and x2 would be making our objective function maximized? Apparently it wouldn't be this, because the x1 and x2 that's on that line is not even feasible. And then the solution would be somewhere here. Sorry, this is not a straight line, but what I'm really after is this line. So this line, it really depends on the specific constraints, the slope, right? So it could potentially be lying on the C. It could be also lying on the D because of the objective function slope. So let's look at here. That's really what we're trying to see here. It is to say that objective function is really some set of parallel lines, and then we have a feasible region, and then we are trying to maximize. If we are trying to maximize, this point is a maximization point, and then if we are trying to minimize, this is our minimization problem, minimization point. That is if our objective function is having this slope. On the other hand, if our objective function is having this slope, then apparently this would be our maximized value, and this would be our minimum value. That is geometric solutions for the linear programming approach. And then next one, I don't know if I still have time. I do. I can spend a couple more minutes here, which is, even though we probably we wouldn't be able to go through the details of the oh, here we're not there yet for simplex method, but here is algebraic solutions. What you can do is find all the intersection points of the constraints and determine which intersection points, if any, are feasible to obtain the extreme points. What is intersection points? Intersection points meaning this would be one of them, as well as the intersection of the extreme points. This will be another intersection point. So instead of just those 4 extreme points, we would have 2 more intersection points. Find all those 6, and then if check if they are feasible. If they're not feasible, they're not going to be extreme points. I hope you understand why this one is not feasible, because this one is not feasible for the first constraint, right? Because the first constraint has to be on this side of the curve, but this point happened to be on the other side of the curve. Okay, so and then you can find all the extreme points. You narrow down those 6 points to 4, and then you evaluate the objective function at each extreme point. Thus, for function evaluation, choose the extreme points with the largest or smallest value of the objective function. But this is not the best approach, because it's an intersection point enumeration approach. That introduces us to simplex method. So what is simplex method? I want to give you a snapshot. That is, you put the linear program into a Tableau format, and then you start with some initial extreme point, and then you test whether some certain optimality is achieved, and also you need to test whether it's feasible if I need to do certain pivot to help me to find the next feasible solution, and optimality test, go back 3 to 5 with optimality test, feasibility test, and pivot pivot is nothing but Gaussian elimination that we studied in high school, meaning that in order to eliminate a certain variable, what type of linear transformation that you need to do to use first equation times 2 minus second equation, things in that nature. That is 3, 4, and 5. You repeat 3 to 5 until you find that you find an optimal extreme point. That is linear program. And then we do need to go through this very carefully next time from page 273 and 278. Today I wouldn't be able to go through this, so we would definitely go through that. And the next thing is sensitivity analysis. What if, two questions, what is the effect of changing the value of the profit for each table? One of the decision variables. And also the second question is, what is the amount of resource available? What is the change of the objective function if one extra foot of lumber available, or one extra foot of labor, one extra unit of labor available, and then it happened to be the interpretation of the extra amount of resource available is called marginal value. Okay, numeric, we're not planning to go through that, but that's pretty much what we can cover today. And then for simplex method, I specifically want to let you know that the first homework that you do on simplex method, you should use use manual solution, not using computer program. You cannot use R to solve that problem. I want you to know how you can do the pivoting. And then unfortunately, maybe next week, if you're interested, can join me in the office hour. I can explain to that this 273 to 278 in further detail next week as well. Okay, any questions so far? If not, we can stop here, and I will see you guys in 2 weeks. Of course, feel free to stop by next week in the office hour. I can explain 273 to 278 very carefully. Okay, have a good evening.